Great. So we are still doing grand canonical example, and we're doing a simple example of three states. So we have epsilon 1, epsilon 2, and epsilon 3. The idea is that we can factorize the system by looking separately on each of those states, right? And we look on the occupation of each of the states, so we can either have one particle with spin up or one particle with spin down. And we are treating fermions. Okay. For those three different states, we obtained that Zi was equal to 1 over 1 minus 1 plus e to the power minus beta epsilon I minus mu. Okay. So this is what we obtained for the partition functions, and generally the partition function of all the system was z1 to the power of 2 multiplied by z2 to the power of 2 multiplied by z3 to the power of 2, and those 2's are coming from the fact that we have spin, and spin can be up or down, plus 1/2, minus 1/2. Those are basically the degeneracies of each state. Now we computed also the occupation probability, right? So the probability of a particle to occupy a given state, so Fi, probability of state or of energy level I to be occupied was equals to 1 over e to the power minus beta, right? Yes. So 1 plus e to the power minus beta epsilon I minus mu. And in general, we can look on this occupation probability as a function of epsilon divided by mu. Here we have epsilon divided by mu. And what we know when epsilon equals to mu, so here we have a 0, 1 over 1 plus e to the power 0, it's 1, so it's just 1/2. And here we have 1. And then we got several limits of the behavior. So we have this limit, very sharp transition. We have almost flat behavior. Okay. And we always have something in the middle. How we can discriminate between those three different behaviors, it depends on this value over here. Okay. So what we write is f 1 over 1 plus e to the power minus beta mu, and here we have epsilon by mu minus 1. Now epsilon by mu minus 1 is our x-axis over here. Now how sharp the transition, completely defined by this parameter beta mu. Okay. So when beta mu is very, very large, right? When beta mu is very, very large, well, it depends on what we make constant, right? So we can make the temperature constant and we can modify mu, or we can make mu constant and we can modify the energy, the temperature. But basically the parameter beta mu defines the sharpness of the transition. So if we can keep mu constant, so what we have, beta mu, which is mu divided by k Boltzmann T. The larger this parameter is, the sharper the transition is. Okay? So this appears for large beta mu, and this appears for small beta mu. Okay? So when the temperature is very, very, very large compared to mu, this is what we have. Okay? So this is high temperatures. And this one, where we have almost a theta, heaviside theta function transition, so 1 and 0, this is when beta mu is very large, so we have small temperatures, low temperatures. Now the only thing that matters to think about how to represent all the solutions are this occupation number. This is the only thing that matters for fermions at least. Why? Because we always look on the different energies, energetic states, energetic levels, and we can always separate them, at least that when there is no interaction between the different particles, and the only interaction is the Pauli exclusion principle. And then, for each energetic state, the only thing that matters is it occupied, yes or no. And what defines the occupation is this number, F, which depends on epsilon divided by mu, if it's high or if it's low, right? And what we see that in the low temperatures, we have an occupation probability which is exactly 1 up to a specific level, and 0 for any energies that are above this level, and the other way around. For high temperatures, what we have, that almost all the different energies have exactly the same occupation probability, which is 1/2. Either they're occupied or not. We don't really have a clue. This value that we see, at least at the low temperatures, that for any energy that it's below this energy, okay, so for T goes to 0, what we have, the sharpness of transition, so for any epsilon below mu, F equals 1. Any epsilon above mu, F equals 0. Okay. So for low temperatures, mu defines the energetic level, that all the energetic levels below this mu are occupied, and all the energetic levels above this mu are empty. Mu is what we call Fermi energy. We have fermions and we have Fermi energy. Sometimes it's also called Fermi level. And it's very commonly used quantity for anything that we want to talk about, say about fermions or electrons, at least at the low temperatures. Okay, we'll see this in a few seconds. So this is what we have done last week. I want to continue a little bit with the discussion of this occupation fraction, occupation probability, and the connection between the chemical potential, mu, and the Fermi energy, and the number of particles that we have inside the system. Now, if you remember, when we started all this grand canonical ensemble business, we wanted to look on systems that can exchange energies. Basically, this was the idea why to develop this ensemble description in the first place. Now, the moment that we have it, right, we can use it and claim that it's actually easier to use the grand canonical description in order to calculate different quantities. So again, for example, if I have those energetic states, about this one, so I have epsilon 1 and epsilon 2 and epsilon 3. Now, the usual question that we solved right now, we don't know what the number of particles is. We know that all the different states are completely independent. We can calculate the ground canonical potential. We can calculate the the partition function, and out of those quantities we can obtain anything like, for example, the average number of particles, and which is d minus d to d mu of psi. We will reconstruct this formula in a bit. So we know psi, and out of the psi and the behavior of psi and its dependence on mu, we can calculate other quantities like n. But we want to make a different statement. Usually we do know n. So this average number of particles, it is known, and in a closed system, or the system where the number of particles cannot really be modified, so we, in a lot of cases, we say that this quantity is known. This quantity is known. Another quantity that enters this psi are the structures, so the microscopic energies. This is something that we cannot modify or control. But then another parameter that we can control is beta, or 1 over k Boltzmann T, or temperature, it also known. Okay. So psi is a function of energies. It is a function of beta, or temperature, and it's a function of the chemical potential. In reality, we usually have to know epsilon 1, epsilon 2, epsilon 3. We control the temperature, we somehow control the chemical potential of the system, or we set it up, and out of this we can obtain everything else, like the number of particles, or the average energy of the system. Okay? But the situation is the opposite. Well, this we cannot control, because this is our system and it's given to us. Well, maybe sometimes we can modify it in the lab, but usually it is set constant. Okay? Temperature is a controllable parameter, and the number of particles is a controllable parameter. Okay? I can put inside my system 4 particles. Okay? Exactly 4 particles, and then I want to solve what actually happens to those 4 particles if I have interactions like the Pauli exclusion principle. I'm not going to solve this saying I have exactly 4 particles. I'm going the other way. I'm saying I don't know how many particles I have. I compute the partition function, I compute the ground canonical potential, and afterwards I know that this number is set. Okay? I can say this is 4. And the moment that I know what is this number, I can obtain other properties and quantities that are hidden inside the system. And you see, the most interesting quantity is this chemical potential, or the Fermi energy of the system. Why? Because you see, the probability function, okay, if the state is occupied or not occupied, what is the probability that there is a particle sitting here? It's completely defined by this function. The energy, well, it's the energy of the state, so this is something that I choose. But the chemical potential, I don't really know what it is. It's not something that I can control. Okay? But if I can find what is mu by solving this equation, by saying I know how many particles I have inside my system, so therefore I can maybe find the chemical potential. This gives me the key to computation of the probabilities. This gives me the key to the behavior of the system at low temperatures, low enough temperatures, where I know anything that's over here is unoccupied, and everything that sits over here is occupied. So the only thing that I really need to calculate is this Fermi energy. The moment I know what is Fermi energy, I know everything. And the way to compute Fermi energy is to solve this equation by setting what is the number of particles that I have inside the system. Sometimes I know the number of particles, sometimes I know the density, but this is a controllable parameter. Mu is not. Okay? So let's see on this simple, very simple example, how do I compute the Fermi energy, at least in the limit of low temperatures. Yes, a question.
לגבי, זה עוד לגבי השיעור הקודם, לגבי ההנחה הראשונית שלנו, שהרמות אנרגיה הן לא תלויות אחד בשנייה. אני לא בטוח שהבנתי את האינטואיציה למה זה נכון. כי אם נלך, יש לי חלקיק שרואה שרמה אחת תפוסה, אז הוא הולך לאחרת. אז זה אומר שהם כן תלויות אחד בשנייה, לא?
Okay, so the question is, it's really confusing that from one point of view we say that the energies are somehow independent, right? But the other point of view will say to us that if this state is occupied, there's definitely is not going to be any particles that will try and penetrate to the state, right? So I got your question correct? Okay. It's indeed confusing, very confusing, but the answer is that when we go to what are the different energies, we count states of this guy. E to the power minus EI minus mu over NI. Okay. Now each state is defined by what is the total energy of the state and what are the number of particles inside the state. So when I say EI, it's not epsilon 1 or epsilon 2 or epsilon 3. EI is what? Is the number of particles, let's call it N1 multiplied by epsilon 1 plus N2 multiplied by epsilon 2 plus N3 multiplied by epsilon 3. Do you agree with me on that? This is a general energy. General, and let's call it N1I, so the number of particles at state 1 for state EI, some general state. This guy and this guy. What is Ni? What is Ni? It is N1I plus N2I plus N3I. Now let's look on this sum over here. So it is minus beta. We have this fraction. So we don't care about the beta. Let's look on e to the power minus mu Ni. It is N1I epsilon 1 plus N2I epsilon 2 plus N3. It's important because it's actually the key. Why I can do all those tricks? It's the point of factorization. N3 epsilon 3. And if you missed it last lecture, it's important to notice it again. So this is the sum of the energies, and I have minus mu N1 at I plus N2 I plus N3 I. Okay. Now let's separate them. I'm sorry it's taking so long, but it's actually quite important. And if you haven't noticed it last lecture, so I will try again. And this is the second trial. So what we have N1I epsilon 1 minus mu plus N2I epsilon 2 minus mu plus N3I epsilon 3 minus mu. Okay. And now your question enters. So this is the again, I repeat the question. We are treating all of system in grand canonical ensemble as if all those three states are completely independent. Right? This was my claim. Somehow I tried to explain it to you last week. But there is an intuitive problem because we do know that when this particle is occupied, the next particle is not going to sit over here, it's going to choose the other two states. So there is interactions, and therefore somehow the states are correlated. But look on this expression.
You get that the chemical potential cancels the dependence?
No, it's not what I'm saying that it cancels the dependence. It's the mathematical structure due to the entrance of the chemical potential that let me treat all the different states separately. Okay? Because we have e to the power minus beta, all of this. And this is a specific state I. What I mean by a specific state I, each state is defined by three quantities, N1, N2, and N3. Okay. And the only thing that I need now to perform when I write it down, so this sum over I, right? And this is Z. The only thing that defines a state when I write it over here is those three guys, N1, N2, and N3. Now, I need to go over all the different states, which means I need to go for all over three triples. Yeah. So all over the different values of the triples, right? But what are the different values of the triples? I have 1, 0, 0, and I have 1, 1, 1, and I have 1, 0, 1, and I have 1, 1, 0, and etc., 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 etc. But because of the multiplicative structure, it's the same thing, because they are all multiplied over here. It's the same thing as, let's look separately on all the values of N1, and let's look separately on all the values of N2, and look separately on all the values of N3. I have a summation, okay, and the only thing that I care is that I cannot take N2 to be 2. Okay? And it doesn't matter what it's N1, N2 can be all either 1 or either 0. This is how I count states. So in this representation, this part is completely independent of that part and completely independent of third part. This means that when I count states, when I compute my partition function, I can treat, and it's a mathematical outcome, I can treat each of the states separately. So the answer is mathematical. Why I can do this? So there is intuition behind it that you can't. Why? Because they are correlated. But then you write it down in this form, and you look on this, but the only thing that I now need to count is all the different N1 and N2 and N3, and it doesn't matter how I count. It absolutely doesn't matter how you count. It means that they are uncorrelated and separated. That's the mathematical description. There is interaction, but the way that the partition function is structured in the grand canonical representation, it lets you forget about it. Okay? It's not that there is no interaction. There is interactions between different particles, but the states are completely independent. Okay? This is the way how we present the partition function that lets us do this trick. Okay, where were I? Other questions before I do this example of computation of chemical potential? Okay. Yes?
If I want to formulate it accurately, is it right to say that the occupations are independent?
The occupations are independent because the different N1s and N2s and N3s are completely independent of each other. Okay? So, does it matter for this occupation if there are other particles over here? You don't care. You have to care. The only thing is it occupied or not? That's it. That's the only thing that matters for this energy over here. Okay. Of mu for a simple example. Now, what is our simple example? We have those three states, epsilon 1, epsilon 2, have epsilon 3. For each particle, there are particles with spin up or spin down, okay, plus 1/2, minus 1/2. And I also say that epsilon 2 equals to epsilon 1. Additional degeneracy. Why? Because, well, you see, even for two states, it's actually quite complicated. Now, I want to control something. Remember, I want to control the number of particles that are sitting inside the system. So I say that n equals 4. Okay? And also, I'm taking the temperature towards its lower limit. All right, so those are the assumptions. This is a simple example. This was simple example. This is even simpler. Why? Only low temperatures are concerned. The epsilon 2 and epsilon 1 are exactly the same level, right? So we have basically a two-level system with 4 particles inside of it, and we're looking on the low temperatures, and we want to see what is the dependence of mu on this number 4, and more specifically on the temperature. Okay. So how we compute this stuff? We know that n, the number of particles, equals to, if we have 3-level system, so we have 2 multiply the probability of f1 plus 2 multiply the probability of f2 plus 2 multiplied with the probability of f3. Okay, so the average number of particles is the occupation of level 1. If it's 0, 0. If it's 1, this is f1 multiplied by 2. Why? Because we have a degeneracy of 2, spin up and spin down. The same goes for the second level, and the same goes for the third level. Okay? So this is basically 2 and 1 average plus 2 and 2 average plus 2 and 3 average. Okay? This is the expression that's written over here. Why it's 2? Because we have spin up and spin down. Great. So it is 2 multiplied by 1 over 1 minus, plus e to the power minus beta epsilon 1 minus mu plus 2 over 1 plus e to the power minus beta epsilon 2 minus mu plus 2 over 1 plus e to the power minus beta epsilon 3 minus mu. Okay, so the moment that we have this, the next assumption was that epsilon 2 equals to epsilon 1. So we can gather together those two expressions. Epsilon 2 equals to epsilon 1, and we have 4 divided by 1 plus e to the power minus beta epsilon 1 minus mu plus 2 divided by 1 plus e to the power minus beta epsilon 3 minus mu. Now moreover, we said that the number of particles inside the system is 4. So all of this equals to 4. Okay, so let's look on this expression of 1 e to the minus beta epsilon I minus mu. We're living in this t to the 0 limit. So beta is a big number. T goes to 0, meaning beta goes to infinity. Now, if beta is a big number, how are we going to expand this 1 over 1 plus e to the power minus beta epsilon minus mu? Okay. So we have two options, right? The first option is when epsilon is larger than mu. And the second option is when epsilon is smaller than mu. Right? So if you remember, it's the same argument we were using for the occupation probability. Below Fermi energy and above Fermi energy. Now, so for epsilon larger than mu, T goes to 0. What is this number over here? 1, right? So, but I don't really take it as a 1, right? Why I don't want to take it as a 1? Because I completely then lose my mu dependence, right? when epsilon is smaller than 0, okay, so let's treat it this way. When epsilon is smaller than 0, this is a negative number. So with the minus over here, it's a positive number. Okay, so we have 1 plus e to the minus beta. It equals to,
e to the beta epsilon minus.
so this goes to e to the beta epsilon minus mu. Right? When epsilon is smaller than 1. No? Something wrong over here? Something right?
You're thinking Taylor not on the exponent, but
Yeah. So what I'm trying to do is the following thing. If I have epsilon mu, which is very, very, very small. By the way, so Ryan, I'm sorry, I think that I made a small mistake. This is not minus over here, this is a plus. Right? Y f I equals to e to the power minus beta epsilon I minus mu divided by 1 plus e to the power minus beta epsilon I minus mu, and equals to 1 over e to the power beta epsilon I minus mu plus 1. Okay? So we have a pluses over here. So we also will expand this. This is why I was getting some weird results and was bothering me. So let's try it again. So we have 1 over 1 plus e to the power beta epsilon minus mu. When we have beta, we have epsilon greater than mu. This is a positive number. Beta is extremely large. So exponent of a very large number is extremely large compared to 1 over 1. So we have over here e to the power minus beta epsilon minus mu. Okay. Now, what happens to the other part? Okay, so what happens when epsilon is smaller than mu? When epsilon is smaller than mu, here we have a negative number, okay, multiplied by beta, which is extremely large number. So all in all, it's a extremely large number. So we have one extremely small number, but a large number with a minus over here. So we have 1 plus an exponent of a very large and negative number. So this is a very, very small number. So 1 plus something very small, we obtain, which is 1 minus e to the power minus e to the power beta epsilon minus mu. Okay? So in order to get this, I used 1 over 1 plus x. It's 1 minus x. Okay? So this is the Taylor approximation that I was doing. Great. So now we can use those expressions inside our formula over here. So the formula is 4 equals 4, 1 plus e to the beta epsilon 1 minus mu plus 2, 1 plus e to the beta epsilon 3 minus mu. Okay, now in order to perform this expansion and utilize those formulas over here, we need to know something about whether epsilon 1 is greater than mu or epsilon 1 is smaller than mu. And the same goes for epsilon 3. Is it greater than mu and is it smaller than mu? Now, what do we know? That in the limit of low temperatures, the lowest states are going to be occupied. Okay? So I can assume, because we have only 4 particles, that somehow they will occupy epsilon 1 and they will probably not really occupy epsilon 3. So we assume that mu is somewhere between epsilon 1 and epsilon 3. This is what we assume, not just assume, but this is the physical guess. Okay? This is the physical guess because we know that when t equals exactly to 0, okay, only the lowest states have to be occupied, and those are epsilon 1 because we have 4 different states there, 4 degenerate states. Okay. So if we have this, we can now say the following thing. We use this expression over here. So epsilon 1 is smaller than mu. So we have 4. When epsilon 1 is smaller than mu, we have this guy. So we have 1 minus e to the power beta epsilon 1 minus mu. Okay. This comes from this term. Now plus 2. And from this term, we obtain e to the power beta epsilon 3 minus mu. With minus, right? Okay. Great. So what do we obtain over here? We open up the parenthesis and we have 4 multiplied by e to the power beta epsilon 1 minus mu equals to 2 epsilon minus beta epsilon 3 minus mu. Okay, let's talk a log out of it. So it's log of 4 plus beta epsilon 1 minus mu equals to log of 2 minus beta epsilon 3 minus mu. Okay, so we have log of 4 minus log of 2 plus beta epsilon 1 plus beta epsilon 3 equals to beta mu plus beta mu. Okay, so look on this. We have epsilon 1 plus epsilon 3 divided by 2 equals to plus log of 2 multiplied by k Boltzmann. This is mu. Okay, so even for this very simple example, which is basically two-state system, we needed to go through the low temperatures and we needed to assume something, etc., etc. But eventually, what we've got, so we've got that mu exactly at t equals 0. So this is our energetic spectrum. So we have epsilon 1 and we have epsilon 3. Exactly at t equals 0, the Fermi energy sits in the middle between those two states or two energetic levels. Okay, this is epsilon 3 plus epsilon 1 divided by 2. This is mu Fermi at t equals 0. As we increase our temperature, okay, so the temperature starts to grow, the epsilon 1 and epsilon 3, they're still exactly the same because we do not modify our energetic levels. But the energy is going to rise up linearly, multiplied by this number, log of 2, as a function of temperature. Okay? At some point, the growth is going to be a little bit different, and in some point, it will also cover epsilon 3. Okay? Exactly at temperature, where at temperature equals 0, only epsilon 1 is occupied. Okay? And as we grow the temperature, the Fermi level is growing up, the probability of occupation spills from epsilon 1 to epsilon 3, and we'll start to see a little bit more and a little bit more and a little bit more from time to time particles that are actually occupying epsilon 3. But all is defined by the value of the Fermi level, of the Fermi energy.
It should be logarithm 2 over 2.
4 over 2.
Yeah, but if you have 2,
We divided by 2 beta.
right side.
What?
We divided by twice beta.
I divide, over here.
Yes.
Thanks. Yes, thanks.
אבל לא באיזשהו מצב כבר מגיע לאזור שה-T הוא לא כאילו 0?
Sure. So this is for very low temperatures. At some point of time, it's going to, this dependence is not going to stay like this forever. It's not. But it is true that the Fermi level is constantly growing with temperatures. This is always true. Right? the Fermi level, it's always going up and up and up and up and up. For small temperatures, low temperatures, it always linear increase. Almost always a linear increase of the Fermi energy. Okay? And it's usually quite difficult to calculate this Fermi energy, okay, for complicated systems. For simple systems like this two-state system or systems where there are no interactions whatsoever, we can compute the Fermi energy, and mostly in the limit of low temperatures. You can say, Stas, I can always solve this numerically, and this is true. Okay, so you can solve this equation numerically. I will give you a temperature, I will give you n, and you will find mu. It can all be solved, but to get an analytical expression, almost always hard. Yes.
If I forget about the degeneracy and we only consider 2, epsilon 1 and epsilon 2, and it looks like that the Fermi level doesn't grow with the temperature.
No. So we have included the degeneracy. You see, the degeneracy was included over here.
Yes. What about if we only have not considered the epsilon 1 equals to epsilon 2?
If you have 3 levels, I cannot solve it. Okay, so I write with the solution. So I cannot prove it to you. Well, there is a proof that it's always a linear growth. But you will have, so you have to solve the following equation. 2 divided by 1 plus e to the power beta epsilon 1 minus mu plus 1 plus e beta epsilon 2 minus mu plus 1 plus e beta epsilon 3 minus mu. And I don't know how to solve it, mu as a function of temperature. Numerically I can solve it, but analytically I can't. That's all. So this is why I went to this very simple, very degenerate case of 2 levels, etc., and we can get this dependence. What can I assure you that mu of t is going to be some constant number, okay, plus a multiplied by t. Okay? So this, for d goes to 0, this is always going to be the case. It's a constant plus a linear dependence on the temperature. This can always be shown, but what exactly is this constant and what exactly is this a, it's already a different question. Yes?
Could a be 0?
Could a be 0? So can we have a t squared? Yes, we can, but you have to work a little bit hard for it. Okay? It's basically, look, try to solve it and you will see. Try to solve it for 4 different states and 5 different states. It's going to be more and more complicated. Yes?
I understand that you took n equals 4 for the sake of example. But
Yes.
Does this calculation hold when n is a small number? Because usually we take...
We will try it in the exam. We'll see. I don't know. The answer is, you see, there are no clear analytical way of solving this equation exactly for any value of beta. There is no. And any values of epsilon 1 and epsilon 2 and epsilon 3. There are some very specific cases when you can solve it and in the limit of t goes to 0. That's it.
I didn't talk about the epsilons. I meant that usually we take the thermodynamic limit.
We will take a thermodynamic limit in the example of Fermi gas. Okay. Other questions? No. Great. So, and one last thing that you have to understand about this Fermi energy and the occupation probability. So this is the occupation probability. And this is epsilon divided by mu. And we know, well, this is 1. And 1 is around 1/2. And what I have shown you that this function occupation probability, well, anybody who learns AI knows that this is related to activation function. There is something that's called activation function, and this form that we use is this sigmoid. If you don't know anything about AI, forget what I said. Forget please what I said. Okay? But this is how the probability goes. Okay? It's called also a sigmoid or logistic function. So it goes towards 1 in this limit. It goes towards 0 in the other limit. Okay? Here it equals exactly 1/2. Now, the form of this function, f of epsilon divided by mu, it is 1 over 1 plus e to the power beta, epsilon divided by mu, minus 1. This is beta mu. Now, this is an exponential decay. So if you stand exactly at this point, okay, we have here mu equals to epsilon, okay? And when we go into this direction, what we have is 1 over 1 plus e to the power beta epsilon minus mu, so it's over here. And when we go in this direction, we have 1 over 1 plus e to the power minus beta epsilon minus mu. Okay. So here we have an absolute value. We can put an absolute value. Okay. So here it's a decay. Here it's epsilon minus mu is a positive number, so it doesn't really matter if we have an absolute value or not. All right. Here epsilon is smaller than mu, so we can put a minus over here, and we take epsilon minus mu as an absolute value. Now, the exponent of any function converges to 0 over here, it converges to a big number extremely fast, and it converges to 0 over here also extremely fast. So we can look on e to the power minus beta epsilon mu only on this function over here. We don't care about 1 and 1 over here. We only care e to the power minus beta epsilon minus mu to the absolute value.
What are you trying to do?
You will understand in a second. So this is epsilon. This is mu. This is e to the power minus beta epsilon minus mu. Okay. I'm focusing on the decay of this function, on the behavior of this function, of the occupation probability, around Fermi level. Okay? I'm at the Fermi level, the probability is always 1/2. I want to understand a little bit more how this probability behaves when the energies are larger than mu and when the energies are smaller than the Fermi energy. Okay? Now, I need to plot this guy. So, it's an exponential decay that goes into this direction and it decays pretty swiftly. And also in this direction, it also decays pretty swiftly. Okay? So the decay here is e to the power minus beta epsilon minus mu. What is the characteristic scale of the decay? What I mean by characteristic scale? When epsilon minus mu equals 0, this is exactly 1. But when epsilon minus mu is around beta, 1 over beta, we are somewhere near 0. Okay? So, when epsilon minus mu is approximately 1 over beta, we have e to the power minus 1. So, majority of the decay already occurred, and this function is what? It's almost 0. Okay? The same goes in the other direction. So, what we understand that the dynamical range of this function, it's 1/2 over here. It's completely defined by the behavior of e to the power beta epsilon minus mu. when e to the power beta minus epsilon minus u, or epsilon minus u, epsilon minus mu equals to 1 over beta, and here epsilon minus mu equals to minus over beta, come over here, okay? This is the dynamical range when there is a modification of this probability. Why? Because there is a modification of e to the power beta epsilon minus mu. So what I'm trying to say that this transition from 1 to 0 occurs not at 1, not at epsilon equals mu, right? But in some range from epsilon minus mu to 1 over beta and epsilon minus mu minus 1 over beta. What it means that this range is proportional to k Boltzmann t to the right and k Boltzmann t to the left. Okay. So when you look on any system and you look on the occupation probability, you can think about it in the following fashion. For very, very, very small energies, extremely small energies, it is always 1. For extremely high temperatures, it is always 0. Why? Because when the energy is very, 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 very small, it's almost probable that somebody is sitting there. When the energy is extremely high, there are no particles with such high energies, so it's never occupied. There is something when the probability is between 1 and 0. And what is this range? It is always centered at the Fermi energy when epsilon equals to mu, around this one over here, and you only can go k Boltzmann t to the right, and you can always can go to k Boltzmann t to the left. So this dynamical range is completely defined by the temperature. Okay? So when the temperature very, very low, this dynamical range becomes very small. So you have a lot of particles or a lot of states that are occupied, small range when there something happens, and then a lot of states which are unoccupied. When the temperature is extremely large, this dynamical range becomes also very, 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 very long, and all the different states becoming occupied. Okay. So this is the perspective of the Fermi energy. Something for fermions occurs only in the vicinity of the Fermi energy. This is the only thing that is important. Where the Fermi energy is located. In the range of 2k Boltzmann t, around this Fermi energy, something happens. The probabilities are not 0 or 1, there is something else. It means sometimes you look on the system and there is a particle. And sometimes you look on the system and there is no particle in the same state. Here, you always look, there is always somebody sitting in the state. Here, you always look and nobody is sitting in the state. Where you have to look and what are the particles that are actually dynamically moving from one state to another, only in this region. Okay? Here the probability is always 1, it's constant, it's independent of time. Here the probability is always 0, it's constant, nobody really there. Somebody, for those energies, somebody coming and somebody is always going. Okay? So this is why the Fermi energy is so important. If you want to remember something, there is something going on around the Fermi energy. What is the dynamical range about the Fermi energy? It's always 2k Boltzmann t. You had a question.
KBT, the x-axis is unitless, so how can you move this k? You divide it by mu or by epsilon?
Take this by mu. This is going to be mu.
So now you need to divide epsilon.
So basically you don't need to divide by anything. You always look as a function of energy. Okay? The short answer is you have epsilon, you have f of epsilon. Here you have mu. Okay? And you always have this behavior. And this dynamical range, this is mu, this is 1/2, and this dynamical range is k Boltzmann t to the right and k Boltzmann t to the left. Okay? Any other questions? All right, so let's try and solve
there any property that can move the range, like using a magnetic field or something like that?
It depends on the system. It actually depends on the number of particles. You will see in a second. So if the number of particles is huge, nothing really can help it. But if you are operating in a system with small number of particles, which are the interesting questions, correlated electrons, the mu can be shifted. So mu depends on the interactions between the particles, in some sense. Okay, we are going to solve the question of Fermi gas or liquid. Okay. It's usually called Fermi liquid, but it's actually Fermi gas. So we have a box. The volume of this box is V. It has n number of particles, or average number of particles. The particles are fermions. Okay. And they are not interacting. And there are no interactions. There are no interactions. Now, when I say no interactions and I say fermions, it's a lie, because there are always interactions, there is always the Pauli exclusion principle. Okay. But it's basically a gas of particles that's sitting in some volume, doing something. And we want to compute the properties of this gas, we want to compute the partition function of this gas, and more specifically, we want to compute the Fermi energy of this gas. Why? Because if I know the Fermi energy, I know the occupation probabilities, I know what is the dynamical range around this Fermi energy, etc. So everything that, if I know the Fermi energy, I can understand anything. Now, we will focus on the limit when T goes to 0, for simplicity. And I also claim that the particles, they cannot simply escape this box. Okay. All right. So how do I solve it? First of all, I have particles. Particles are free. They are fermions. So I have to treat them quantum mechanically. Okay. Now we all know how to solve. I hope you all know how to solve Schrödinger equation, right? And Schrödinger equation, we have different energetic states of free particles, which is p squared divided by 2m, which is h bar k squared divided by 2m. These are energies. Okay? The energetic spectrum of a free particle are cosines or sines, right? Or generally e to the power I kx. But since we are constructing the system such that the particles do not get out of this box, there are boundary conditions, okay, for those waves. And the boundary conditions basically state that those, not just any wave inside the box, but only standing waves. Why? Because the probability density that we obtain from the Schrödinger equation, the wave functions, are going to be 0 outside of the box for each particle. Okay. This means that we're looking on standing waves inside a box of volume V. Now, those two statements are completely enough with the knowledge that we already gain during this semester to exactly solve this system. So first of all, we say, what is the partition function? So the partition function is because all the different states, each state depends on a specific k, the k vector or the wave vector of each of the particles. All the states, we treat the system in a grand canonical fashion, as we did before. All the different states, not the particles are interacting due to the Pauli exclusion principle, but all the states are not interacting, right? So if all the states are not interacting, we have just to multiply by k, okay? What we are multiplying by k, the partition function of each of those states. If you think about it, I have epsilon of k, and I have epsilon of 1, and I have epsilon of 2, and epsilon of 3, etc., etc. And each of those states, well, there's of course a continuum spectrum, but each of those states are independent, and I can treat, as in the previous example, I can treat them independently. If I treat them independently, the only thing that I need to, in order to compute the partition function, are the partition functions of each single state. So I call them zk up and zk down. Okay? So I'm assuming that I have fermions and the degeneracy is plus 1/2 and minus 1/2. Okay. What is z of k 1 up? So I'm looking on state with a specific k. Okay, I'm looking on, with a specific k, and I'm saying the following thing: it's either unoccupied. Okay, so I'm going over all the different states, and I'm computing I to the minus beta epsilon k minus mu. And here I have nk. Let's write it. Sum over e to the power minus beta n of k epsilon of k minus mu. This n of k is the number of particles that are occupying my state. I'm sorry, my level. It's not a state, but the level. So it's either 0 or 1. So it is 1 because when nk equals 0, I have e to the power minus 0, and it's 1, plus e to the power minus beta epsilon of k minus mu. Okay. So I can write it down as e1 plus e to the minus beta h bar squared k squared divided by 2m minus mu. Now, what is zk down? It's exactly the same because the energy that I put over here, it's independent if the spin is up or the spin is down. If I had some external magnetic field, it's going to affect the system. But we don't have external magnetic spin field. So zk down also equals to 1 plus e to the power minus beta h bar squared k squared by 2m minus mu. So we all know that what is zk down, zk up, and we can say that z equals the multiplication over all the different levels that we have inside the system, 1 plus e to the power minus beta h bar squared k squared divided by 2m minus mu to the power 2. 2 is the degeneracy of each of the levels. Right? This is the another bracket. Yep. Great. What happens next? Next, right? So we want to compute, for example, psi, which is minus 1 over beta log of z. Okay? We want to compute the grand canonical potential. This is the standard way to go. Z, so we have a log of z. So it's psi equals minus 1 over beta, a sum over all the different k's, log of z k. And here we have 2. Or let's put it over here, 1, and here we have 2. Very nice. But what are the different Ks? Right? So we have a lot of Ks over here. We have a summation. Moreover, Ks, the spectrum is what? Is we can assume it's continuous. So all of this, psi equals minus over beta. Let's take the 2 out. So we have minus 2 beta, an integral of log of z of k, d, some density of the levels, right? So we have d over k dk. And k in general goes from 0 to infinity somehow. What is this d of k? What is this d of k? Standing waves inside a box of volume V.
Proportional to k squared.
Sorry?
It's something that's proportional to k squared.
No. Well, yes, almost. But we know exactly what d of k is, or d of epsilon is, right? Exactly, because we derived, and we spent something like an hour, or even more, to derive the density of states for standing waves for the bimodal, right? Now, the only thing that matter to us are how many standing waves can live inside a box. Now, does it matter that those standing waves describe oscillations of matter, or they describe the solution of the Schrodinger equation? It doesn't matter. It absolutely doesn't matter. The only thing that matters is how many half wavelengths can sit inside a box. That's it. That are the different states. If those are real fluctuations of real space, or those are fluctuations of an imaginary function that is the wave function, a solution of Schrodinger equation, absolutely doesn't matter. Okay. So this d of k, and let's write it d of epsilon. Okay, we don't use the omega over here, we have epsilon. It's going to be exactly the same, which is the volume divided by 2 pi squared k squared dk of epsilon d epsilon. It's the same formula as we had for the Debye model, because these formula occurred when we computed the number of states of standing waves, and it's completely irrelevant that what those waves describe. Yes, the question.
כאילו, לגבי הצפיפות עצמה, האינטואיציה הראשונה אמרה לי שזה יהיה כזה רכבת עלמים של כל האומגות האפשריות, כל ה-K האפשריים. ועכשיו זה כזה...
So the question is, I had an equation that there is going to be a sum of all the different K's, but this is exactly what I've been trying to do here. Right? So I know that any state can be separated in different states, but what are those different states? Simply standing waves. So if I had, so psi here is a grand canonical potential, but if I had a Schrodinger equation and I would write it as a solution, it's going to be a sum e to the power ikx, right? What are those eikx's? Sinuses and cosinuses. And we have boundary conditions. The same thing. Exactly the same thing. Exactly the same superposition. Schrodinger equation. And you have to understand it in your mind. It's a wave equation. It describes waves. Okay? So when Schrodinger described it, he thought, well, we have a de Broglie particle wave, so I will write a wave equation. It's a simple wave equation, and the solutions are always waves, and the superposition principle always applicable to a solution of Schrodinger equation. So this is why it works so neatly. Okay? This is why I can use this representation. Yes?
Shouldn't the integral be 3D? Because like the k is a wave vector, so
Okay, not exactly. Why? Because k depends on the energies. And the only thing that defines a wave in the Schrodinger solution is the energy. Okay? So this is why we don't have all those threes that we had in the Debye model. you're right, in the Debye model we have 3's because there is this way and that way and that way. We don't care. We have a epsilon and k.
סטאס, נראה לי שכאילו, לא מה שמעניין.
I have to continue forward. I have to continue forward. We have 15 minutes. I understand that it's a lot to grasp at one time, but we have to go forward. All right, some integrals. So first of all, so let's write it down. This d of epsilon, let's write it d of epsilon, v divided by 2 pi squared. Now k squared is what? K squared is 2m divided by h bar squared epsilon, right? And what is dk to d epsilon? Multiplied by, so let's dk epsilon to d epsilon. Now k epsilon, k of epsilon is 2m h bar
No, 2m epsilon. Divided by h bar is square root.
2m epsilon 1 over h bar square root. Yep? Okay. So dk of epsilon to d epsilon is 1 over h bar, a square root of 2m multiplied by 1/2 multiplied by 1 over square root of epsilon. Okay? Let's put everything inside now. So psi is minus 2 over beta, an integral from 0 to infinity of log of z of k. What is z of k? This guy. So it is 1 plus e to the power minus beta. Now instead of h bar k squared 2n, I'm writing epsilon minus mu. I close the parenthesis. What I do have next is d of k, which is d of epsilon. And we write it as v 2 pi squared 2m epsilon divided by h bar. And I have, and what I have next, and I have this square root of 2m divided by h bar multiplied by 1/2 1 over square root of epsilon d epsilon. H bar squared. So I don't have h bar squared.
No, you should have.
I should have.
From the formula. Before the decay to the.
So here, here h bar squared. Yeah. Okay. All right. So what do we have? Minus 2 over 2 goes away. Let's take everything that is independent of epsilon and beta. Let's take everything out. So we have 2m divided or 2m to the third power, 3 over 2. We have h bar to the third power. We have v, we have 2 pi squared. We have 1 over beta, an integral from 0 to infinity of a log of 1 plus e to the power minus beta, epsilon minus mu. And we have here epsilon to 1/2, right? Epsilon to 1/2, d epsilon. This is the grand canonical potential for the Fermi gas. Right? The moment that we have written a formula, everything else can be obtained from this formula by taking some derivative. Right? We want to compute n, we want to compute u, we want to compute anything, just take the appropriate derivative out of this function over here and you're done. Okay? So it's easier said than done, of course, But this is the only thing that we have left.
But the integral was with respect to k, not to epsilon.
So you think that there are an additional something over here.
Yes, the constant.
Okay, I will come to this point a little bit later. Okay. Why there shouldn't be any constant. Okay. Remember, our goal was to compute mu. And what it was written over here beforehand is that n is a constant. So how we compute the Fermi energy for this Fermi gas? We compute the average number of particles, and we set it to a constant, okay, and we solve it with respect to mu. Now n is always minus dou psi to d mu. Okay. Minus d psi to d mu. If you don't remember this specific form over here, you forgot the derivatives, your whatever, you can always go to the probability description, right? So from probability, what do we know? We know that n, okay, average, it's a sum over all the epsilons, and we have n epsilon multiplied by 2, and this is the average. Okay, so the average number of particles inside the system equals to the average number of particles at each state multiplied by 2. 2 comes from the degeneracy, okay, because we can have energetic level with spin up and energetic level from spin down. So this is why 2, right? So it's basically the average of a sum is a sum over averages, always handy. Now, then we only need to compute an epsilon, okay? An epsilon average. What is this an epsilon average? We know this guy. It is e to the power minus beta epsilon minus mu divided by 1 plus e to the power minus beta epsilon minus mu, which is 1 over 1 plus e to the power plus beta epsilon minus mu. Okay, so we have to plug this result into here. And remember that it's not a sum, but it's an integral over all the energetic states. So n equals to an energy that goes from 0 to infinity of 2 multiplied by 1 over 1 plus e to the power beta epsilon minus mu. And here we have d of epsilon, d epsilon. This guy will always appear when we consider fermions. It's called Fermi-Dirac distribution. Okay. So in order to compute something, when you use fermions, you always say, well, I'm summing over all the different states. I have a Fermi-Dirac distribution over here, okay, and multiply by the density of the states. Where from this Fermi-Dirac distribution appears, it always appears from some average number of particles, average energy, average something. And when you average something, you always get this guy. Based on the occupation probability. Okay, now d of epsilon is the same d of epsilon that we had over here. This guy. Okay, so we have n equals to from 0 to infinity 2, 1 plus e to the power beta epsilon minus mu. And here we have whatever we have over here. So it is v by 2m 2 pi, I'm sorry, 2 pi squared. We have this prefactor. 2m to the power 3 halves divided by h bar to the power 3 e to the power 1 half d epsilon. Okay, so either you compute psi and you remember that there is a derivative because you have all those, you have a book on you or something, or you remember how those ground canonical potential works, or you can always say, well, for probability it's always easy. The average of a sum, it's always a sum over averages. Doesn't really matter what you do, eventually you still have to compute this nasty integral over here.
You forgot a half
I forgot a half. Where I forgot a half?
in the d of omega, because we had there 2 over beta and there.
Yes. But this 2 is this guy. In total. In total. So I don't have a half. Okay. Where is this 2? No, I think I'm fine.
So we have to.
I have a hat. I had a hat from here. Yes. Thanks. All right. Now, we are interested in the behavior. So this n is set. We do the following thing. N is set. Mu is not known. We can control beta, the temperatures. Epsilons, well, it's a parameter of the integral, so we don't care what it is. Okay. And we want to compute this integral at least in the limit when t goes to 0. T goes to 0. So what do I know when t goes to 0? What I know exactly when t equals to 0. So when t exactly equals to 0, I know that this guy, where this guy came from, 1 over 1 plus beta epsilon minus mu. This is the occupation probability. This is the occupation probability. Okay. So this occupation probability, when temperature, let's call it f of epsilon, it's extremely sharp. It is 1 when epsilon is smaller than mu. It is half when epsilon equals to mu. And it's 0 for any epsilon that is larger than mu. Let's call it mu Fermi. This f of epsilon. Okay. So we know that when we integrate over all the different epsilons in the limit of very small temperatures, we don't integrate up to infinity. N goes from 0 to mu Fermi. This probability over here is what? Is 1. Okay. Multiplied by v, 2m 3 halves, 2 pi squared, h bar to the third, epsilon to 1 half, d epsilon. So we have n equals to v 2m 3 halves 2 pi squared h bar to the third, an integral from 0 to mu Fermi epsilon to power 1 half d epsilon. A nice trick, right? So we use physics in order to compute this integral because we know that this guy over here has a very distinctive form in the limit of very low temperatures. Okay, this integral is already simple, right? An integral equals to, we have 3 what?
2/3.
2/3.
You need to call the constants and then
Well, what constant?
the v2m.
So let's see. 3 halves divided by 2 pi squared h by to the third And what we have here is 2/3, right? E mu Fermi 3 to the second power. Okay, so mu Fermi equals to so what we have over here. So n multiplied by 6 pi squared h to the third. Not by 6, 3. 3. And here we have 4 pi squared. V to m 2 4 to m 3 halves, and we have v. All of this 2/3.
What is the 4? How did you get the 4?
I don't know. No 4. No 4. Okay. Now, if we take a box. Okay, so look on this. This is in the limit of very small temperatures. Okay. Now, the thing to notice is that n is extremely, extremely large. The number of particles is in the order of 10 to the power 23. So what we can say that mu divided by k Boltzmann, okay, why divided in k Boltzmann? Because I want to obtain an effective temperature. So mu divided by k Boltzmann, okay, it's on the order of 10 to the 4 up to 10 to the 5. When I include a regular volume, I take into account the h bar to the third and the mass of the electrons. I put all of those guys inside. So what is this? This is mu divided by k Boltzmann. I can say that, let's say that this is, let's call it T effective. So mu Fermi is k Boltzmann multiplied by some T effective. Okay. In order to get the units of an energy, I need a units of a temperature over here. Okay. So think about it. I have taken particles, I set a temperature which was extremely low, and I ask what is the Fermi energy. Why do I care about the Fermi energy over here? Okay? Because everything is defined by Fermi energy. And what I get that the Fermi energy is as if the system had an effective temperature of 10,000 Kelvin. Okay? Now where it's coming from? It's coming from a lot of particles from this n over here. Okay? What this means physically, not mathematically. Mathematically I got a big number, right? I got a huge number. Where this large number is coming from? We know that if this is our electronic spectrum, all the low energies are occupied up to the mu Fermi. So we have particles, we can say, sitting one on top of each other. Now, why? They are trying to occupy all the lowest energies possible. Now, I occupy this energy, the next one is also occupied, the next one is also occupied, the next one is also occupied. So all the different particles are going to do what? They're going to extend this energetic spectrum all the way up to the effective temperature of 10 to the 4th. 10 to the 4th multiplied by k Boltzmann.
Why would it be 10 to the 4?
Sorry?
Why would it be such a large number?
Because n is extremely large.
Okay.
Right? So the big number here, so we have h bar, it's small, but m is also small. They somehow cancel each other, etc., etc. The big number is n. If I had very small number of particles inside a system, this mu Fermi would be small. Right? So the big number n over here, it also defines the large scale of up to where I fill up all my energetic levels. Now, so this is Stas, it's great. You computed something for extremely low temperature, okay? And you had no interactions whatsoever inside your system. You cannot solve this if you will include interactions, right? So I had a gas of particles. The solution to the Schrodinger equations were waves, but you include additional interaction inside your system, and all of this description is completely lost. You cannot solve the Schrodinger equation. You cannot use the density of states, this d of epsilon that you use. You can't do anything. Even your separation of energies won't hold. Okay, so this is nice, but it all holds only for very, very dilute, not dilute system, but system of non-interacting particles. But it's not true. Why it's not true? Because if I only have Pauli exclusion principle, you see, I fill up all the different energies up to a very large number. So let's assume I will include additional interactions between the particles. Okay? I will say this particle and that particles, they also repel each other or they attract each other. They do something to each other. Because this number is extremely large, those additions are going to be negligible. You don't care about those small additions of interactions between the different particles. The Pauli principle still will force everybody to fill up all those different states, and the interactions won't matter. So as long as n is large and I have a sea of particles, the thing that they are interacting somehow is completely unimportant in the limit of low temperatures. And also in the limit of high temperatures. Because, well, there's going to be small fluctuations about this large number. But those fluctuations are going to be small. Why? Because the interactions are not extremely large. Everything is defined by the Pauli exclusion principle. So, indeed, we solve a very simple case for which we can compute mu of Fermi and we compute everything. But the fact that we get such huge number for the Fermi energy, it tells us that inclusion of additional interactions between the particles won't matter a bit. This is actually what we can see in experiment. Okay? When it does matter, when this mu of Fermi is small. So when mu of Fermi is small, interactions start to affect everything. They're going to modify mu of Fermi by a lot, and this becomes important. But when mu Fermi is large, and you perturb the system, you add something else, which is small compared to this number, it doesn't really matter. So it's not a mathematical proof, but it's a physical claim that actually holds in any experiment. Okay, so we will continue a little bit about this discussion of filling up all the different levels on Tuesday.
Thank you very much.
Oh, not this Tuesday. Next Sunday. Sorry. Okay.